In this screencast, we're going to discuss using nonlinear least squares. So in the previous lecture, we used linear least squares to fit an equation to experimental data. And the equation might have looked like this, where y equals mx plus b. Or if you have multiple inputs, like x1, x2, all the way to xm, you also have multiple unknown parameters, more than just two. So you have a0, a1, a2, all the way to am, where a0 doesn't have an x associated with it. But in this lecture, we're going to look at the case in which the equation is nonlinear with respect to the parameters, because these equations are linear with respect to the parameters a, I, and also b and m in this particular equation. So in this first example, 14.1, we're going to look at a bell-shaped fit to the dorsal concentration. So this is the kind of work that I do in my lab, where if you have a 2.5-hour-old fruit fly embryo, the concentration of a protein called dorsal is distributed in an approximately bell-shaped curve, which looks like this. Right? And here's what the real image looks like. So the dorsal protein is highly intense down here. This corresponds to the peak of the bell-shaped curve, and then as you go around the periphery in this what we call an x-axis, it is high and then it drops off to low. Okay, and the bell-shaped curve can be approximated by this equation here. Or note that you have these parameters. You have a, which stands for the amplitude of this curve. You have mu, which stands for the location of this point on the embryo. You have sigma, which corresponds to how wide the curve is, and then you have b, which corresponds to how far above zero it is out here. Now the details aren't important for you, but the point is that this equation is nonlinear with respect to the four parameters. And what we're trying to do is we have this experimental data, and we want to fit this bell-shaped curve, find the best fit bell-shaped curve so that we can find out what these parameters are for each embryo. Right? So given these measurements x and y, in other words these dots here, these gray dots, we want to find c of x here. So how do we do that? Well, because this equation is nonlinear in the parameters, we can't use any of the methods that we've talked about before. And so also we'll have to find an iterative solution. So the first step is to define the error associated with each point I. Right? So as before, we have this error term, which I'm going to call epsilon sub I, and that's equal to yi minus c of xi, or equal to yi minus a exponential of minus xi minus mu quantity squared over 2 sigma squared plus b, although that's actually minus b because it's minus both terms, right? Okay, and so for each point xi, yi, this is the error if we are given values of a, b, sigma, and mu. So next we're going to define a function f that is the sum of the square of the errors. So this function f, it takes in all of our data, but typically we just write it as a function of a, b, sigma, and mu. But it's a function also of all of our other data points as well, technically. But that's equal to the sum I equals 1 to n of epsilon I squared. Or if we're going to write this all out, sum I equals 1 to n of the quantity yi minus a exponential minus xi minus mu quantity squared over 2 sigma squared minus b. All of that squared. Now as before, what we did before when we had an equation like this is that we took the partial derivative of this equation with respect to each of the parameters. Before it was yi minus mx minus b, right? And so we took a partial derivative with respect to b and a partial derivative with respect to m, and we set those equal to 0. And those were our constraints on finding the best fit values of m and b. So in the same way, we're going to do that here. So the partial derivative of f with respect to a is equal to 2 times the sum I equals 1 to n of epsilon I times partial of epsilon I with respect to a. And that's the one for a. So remember, this is exactly how we started out doing it with simple linear least squares, right? And we had this term where we had 2 times this sum times of epsilon I times the partial of epsilon I with respect to the parameter we were differentiating against, right? So similarly, we have the partial of f with respect to b equals to equals to the same kind of sum as the one for A, except for now the partial inside the sum of epsilon is now with respect to B. Of course, we can write the same kinds of partial derivatives with respect to the other two parameters, and they will end up looking like this, which is just the same thing as what the other partials with respect to the other two parameters look like, except for, again, now you have the partial derivatives inside the sum with respect to the individual parameters, which are different. Okay, so this is what we had before, just like in simple linear least squares when we had partials with respect to B and partials with respect to M. And then we set both of those equations to 0 and found what the best values of M and B were. The difference in this case, though, is that in the other case, those equations were linear, and so we could just quickly solve for them and find a very simple formula. And in this case, these equations, if you plug what these partial derivatives actually are into the equation, they're going to be nonlinear. And because they're nonlinear, it's going to require an iterative solution, right? So what you get now is you get a set of 4 nonlinear equations with 4 unknowns, right? And so what you have is you have your 4 unknowns being A, B, sigma, and mu, and you have this set of nonlinear equations f of y, right? So remember, just like I just said, y is equal to A, B, sigma, and mu, right? And your f of y are these 4 equations. These 4 equations here, like shown. And so, but don't be weirded out by all of this. I mean, these are just equations that you can write down when you know what your g of x is, or in this case our c of x, which if I scroll back up to here is just this, right? So we can take partial derivatives of this equation with respect to a, b, sigma, and mu, and plug in values for xi and yi for each one of these. And what you get is you get these 4 equations here, or these 4 terms, epsilon I times a partial with respect to A, epsilon I times a partial with respect to B, and then add up each one of those for each value of I going from 1 to n. And then you get this equation, or this vector valued equation, a system of 4 nonlinear equations and 4 unknowns, where here are your unknowns. Again, so we can solve this just by any other way of solving a system of nonlinear equations, right? You can use solver, you can use Newton's method, we can use fsolve, etc., all the things that we've already learned to do it. And so what we're going to do then is, in order to optimize f, or to minimize f, the little f, we need to basically employ solver or Newton's method or something like that on this equation here for this equal to 0. Now, in addition to that, of course, we could also stop at the level of little f, which is this guy right here, right? Little f, and then instead of taking all these partial derivatives and trying to solve 4 nonlinear equations and 4 unknowns, all we're going to do is we're going to take this guy little f, and we're going to plug him in to one of MATLAB's nonlinear functions, minimizers like fminsearch, or some other optimization package like LSQ nonlin and fit, which we're not going to talk about in this class, but for anyone who's interested, they're out there. Or you can use solver for this, right? Now in this class, we're not going to tackle anything this large for it, right? But I just want to show you what nonlinear least squares looks like in these kinds of cases.